Welcome back to session 20 on absolute maximum shear stress, and this is the second part. In this portion of the session, we're going to discuss how we can use Mohr's circle to calculate absolute maximum shear stress. And to kind of illustrate this principle, we're going to essentially start with an element, and we're going to say that it has positive in-plane stresses. What does this mean? It means that sigma 1, we'll call it, as being the larger of the two principal stresses, is greater than 0, and it's also greater than sigma 2, which is also greater than 0. Okay? And sigma 3, though, we're going to say is equal to 0. So, the first portion, we were saying, oh, maybe we can do some things in 3D. We are, okay, and we're going to right now, but we're thinking about stresses on a planar element. Okay, so these are plane stresses. So what does it look like? Well, here we can draw a sigma 1, okay, in the x-axis, right? This is one orientation, right? We could have flipped sigma 1 and sigma 2, but here we're talking about this being the x direction, this being the y direction, sigma 1's in the x direction, sigma 2's in the y direction, and to keep the right hand rule, we have a z-axis where sigma 3 is equal to 0, essentially, okay? So if we want to draw this depiction on Mohr's circle, what do we see? We see, well, that we have a sigma 1 and a sigma 2. And sigma 1 is greater than sigma 2. So, maybe sigma 1's over here, sigma 2's over here, like we see here. And then we can also draw a Mohr's circle through these points, right? So here's a sigma 1, here's a sigma 2, and this is the Mohr circle. And this is what we did in the last session. But we're going to think a little bit now about not just what is the maximum in-plane principal stresses, or what are the maximum in-plane principal stresses. We're going to think and the maximum in-plane shear stress. Sorry, I'm a little tired. We're going to think now, what happens if we look at a different perspective, a different plane? So let's take that element that we just had, and now we're going to essentially rotate it to the right so that Z is now facing to the right, okay? And X is now going in to the board, like you see here. Y is still in the Y direction, okay? And so now we take a planar cut. And what do we see? If we're, using Mohr's circle with plane stresses, we have a YZ plane, and sigma 2, once again, is there, and that's in the Y direction. There are no stresses in the Z direction, and this is planar, so we're going to ignore the sigma x that we were looking at as sigma 1 in the first case. Or same case, but first orientation. So what would this Mohr circle look like if you had to draw it? So if we're drawing a Mohr circle, well, we have a sigma 2, and we have sigma 3 equals 0. The sigma z is equal to 0. So sigma 3 was put down here, right? That corresponds to there not being stress in the normal stress in this z direction. And the Mohr circle that we draw, okay, is similar to the first one, right? But it's going through now sigma 3, which happens to be at the origin. So now we have two Mohr circles. We were just looking at, in the last session, when I said before, we were just looking at a planar representation. Now we're looking at multiple planar representations on Mohr's circle. And you guessed it, here we go again. We're going to do one more. All right, so what is this? This one, okay, is maintaining sigma x or sigma 1 in the x direction, right? But now what we've done is we have taken the sigma z that was coming out and flipped it up. So now it's flipped up. This is sigma z that was coming out, now flipping up. And y, since it was up and then we rotated it 90 degrees about x, and at least the way this is actually, we're negative 90 degrees about x, the way this is depicted. Okay, we now have z pointing up and y going in. Here is sigma 1. This is our stress that we can see on this element, right? So it's going to get involved with our Mohr circle. What is sigma z? Well, once again, that's equal to 0. Sigma 3 is equal to 0. So if I want to draw this Mohr circle, I'm going to be using my sigma 1 and I'm going to be using 0. And maybe I could use a different color. Okay, I know this is orange and this is red. They are very hard to distinguish. And look at this. The Mohr circle, though, that goes right from sigma 1. Sigma 1 was declared to be the largest. Okay, sigma 3 is at the origin. This is the corresponding Mohr circle for the xz plane. Now, before we were defining the maximum in-plane shear stress, right? We were looking at the radius of a Mohr circle and then we were figuring out what the maximum shear stress was. Yes, we can do a similar thing, but now we have 3 circles. And so if we want the absolute maximum shear stress, we want to see, or we want to look at which one of these circles is the biggest and will provide the most shear, right? Or the maximum shear. So here's a tau max xy, okay? That's saying that, okay, it's associated with this one that we had up here in the xy plane. Here's a tau max yz, okay, or zy, would be fine. This is associated with this plane that we have here, and we have a tau, actually we'll call it absolute max because it is the biggest circle. Okay, so it will have the largest shear stress, and this is in the xz plane. And we can rewrite these expressions as we see here. And this is for the case we've assumed that both principal stresses, I mean, I guess we can say there are 3 really, but the 2 that were kind of non-zero, they're both positive. And so look at this. Tau max xy, so that's this one right here. It's sigma 1 minus sigma 2 divided by 2. Yep, that looks right. That's the radius here. Tau max yz, all right, so yz is this purple one. That's the sigma 2, okay, minus 0 divided by 2. Okay, so that's this one. And the tau absolute max is associated with this orange circle, right, where we have a sigma 1, okay, coming around and then working with sigma 3, which is 0. So this kind of idea of being able to take a planar stress element and just look at the maximum in-plane shear stress to determine the shear stress that, the most shear stress that the material might be experiencing is not necessarily the way to determine the maximum shear stress that it's experiencing. Okay, it's possible to have the in-plane shear stress, the maximum in-plane shear stress, line up with the absolute maximum shear stress. Okay, there are configurations that occurs, and that's fine. But there are many conditions, many situations where that does not occur. Okay, so this is a nice way, if you have the principal stresses, to be able to figure out what the maximum shear stress is using a graphical technique. Very little math here, as you can tell. Now, what happens if you have one positive and one negative in-plane principal stress? So let's say that we have something here where sigma x or sigma 1 is positive and sigma 2 is negative in the y direction. So what is this Mohr circle, or what is this set of Mohr circles look like? We can say that we have our sigma 1 and our sigma 2, right? Sigma 2 is negative now, and we can begin to kind of think about, okay, what is the Mohr circle associated with this particular orientation of the element? Well, we have a sigma 1 and we have a sigma 2. Sigma 1 is positive, sigma 2 is not, it's negative. But the circle is just going to go around, it's going to go through both of these. So that's one representation, and that actually ends up being the absolute max, all right, as you might guess, because if we have the consideration of another principal stress, it's going to be sigma 3, or sometimes this might be called sigma 3 and this would be sigma 2, but it's going to involve this stress at the origin. And so let's say that we go from having this x, y, where z was coming out of the board, and now we'll say that we're going to kind of flip orientations around and have this xz plane, right? So we still have our sigma 1, and now we have our z coming out the top, but there was nothing coming out of it when it was facing us. So we just have sigma 1 and 0. And that's what we've drawn here in the green. And in this case, since the sigma 1 and sigma 2 are with opposite signs, it actually ends up being less. All right, so this circle is inside the purple one. And tau xc is equal to sigma 1 over 2. Similarly, we can see that if we have our yz plane and we have our sigma 2, okay, which was coming into the negative y, or was within the negative y direction, right? That still is there, still powerful, but now sigma z is also equal to 0, right? So you're looking at a 0 here and a sigma 2 here that might be negative, and it's at this point. So we can draw our third Mohr circle in there, and we can write tau yz is equal to minus sigma 2 divided by 2. So it's important to not just, how do you say it, only use the formulas. I mean, you can, all right, but you have to be very careful, okay? And you should graph things out, because sometimes, like in the previous example, sigma 1 and sigma 2 were on the same side of the tau axis. But in cases like this one, you can actually have, and so in the earlier case, essentially the principal, the maximum principal stress was related to, or the stresses were related to like a sigma 1 and a 0, right? And so the absolute maximum shear stress is going to be just the sigma 1 divided by 2. But in this case, the maximum absolute shear stress is the sigma 1 minus the sigma 2 divided by 2. So here's another example for this set. We have sigma x equals 100 megapascals, sigma y equals 50 megapascals, and the rest of the stresses are equal to 0. So this is a state of, we have condition for principal stresses. And sigma 1 equals sigma x equals 100 megapascals, sigma 2 is equal to sigma y is equal to 50 megapascals. Excuse me, and sigma 3 is just equal to 0. So when we draw a Mohr circle in this case, what are we going to do? Well, we often just get in the habit, you can think about the planes every time, but once we've gotten the principal stresses, I usually just think, okay, plot them on the horizontal axis, the sigma axis, and then have some fun. start drawing the 3 circles that you can draw with these 3 points. So we do that and we say, okay, if we think about things a little bit, we're like, okay, well, that's the XY plane. And if we think about this one a little bit, this is the YZ plane, okay? And the big one, though, is going to be the XZ plane, all right? So this was 100 megapascals, and this is 0 megapascals. So the XZ plane is going to give us a diameter, right, of the Mohr circle, which is larger than the diameter of these smaller circles. And its diameter divided by 2 is the radius, and that radius is going to correspond to the absolute maximum shear stress. Okay. Now, question 3 gives an opportunity to look at an element with sigma x equals 100 megapascals, sigma y equals minus 50 megapascals, with the other stresses being 0. And the question is, what is the absolute maximum shear stress? Okay. And then the 4th question is, take a look at an element with sigma x equals 100 megapascals, sigma y equals 50 megapascals, and sigma z equals 10 megapascals, and figure out what the absolute maximum shear stress might be. Okay. Yeah, in this case, you can use Mohr circle. You don't have to go to the scripts. You can just use Mohr circle. You have 3 points that are normal, or 3, yeah, I mean, you can call them points, but 3 markers that you're going to put on the horizontal axis for principal stresses on Mohr circle, and then move from there to figure out what the absolute maximum shear stress is. Right. Well, thank you for your time, and that concludes the second part of our discussion on absolute maximum shear stress.